Right, we are on video lesson 3 for AP Precalculus, and I hope you know that that's Willy Wonka, right, as a joke, but what if I told you that slope and rate of change are the same thing? I hope you know this from this week. I want to run through some practice problems and have you practice this one more time because this is such an essential thing. Okay, we're going to really, when we talk about functions, how one variable changes the other, right? This concept of changing is going to be something that we look at all year, and we want to make sure we have this down. And sometimes I think students feel confused, and it's really not. It's not a complex topic. So let's practice a little bit in this. Oh, this shouldn't say meeting anymore. This should say video lesson. If you haven't noticed, last year I did have a live session. I didn't have time to do a live session this week. That's why everything is changing from live videos to video lessons. So if you see it not right, you'll understand why. All right, so what are we going to do? We're going to review our goals and see from this past week and see what you should get done next week. We're going to do some practice with these properties of functions one more time, just to make sure you got that down, and a little bit more practice with rate of change, and then you're going to be ready for week 4. So let's switch over to next week. So week 3, right? You finish these lessons on rate of change, transformation of functions, composition of functions, and you've taken a quiz, right? As long as you do corrections by Sunday evening, right, you earn points back from your quiz. So make sure you get to those, and remember there's always extra practice. So after you get through this week, if you feel like I still want to practice a little bit more, it's here. If later in the year you just want to review, you can always come back to the weeks for extra practice. All right, so next week is we're going to work on inverse functions. So there's a lesson on inverse functions. There's going to be a lesson on modeling with functions. And then I broke this up into 2 parts. It's a little bit long. So one is the lesson and one is the practice. So they're separate. There's going to be a quiz on the College Board website. So you'll go there and you'll take the quiz, and then you'll come back and you'll report that you've done it and show me your work. And it won't be a Zoom meeting, remember, it'll be a video lesson. So next week we're kind of wrapping up Unit 1, Section 1, right, with a second quiz. Okay, so that's where we're at. Let's go back to here, and let's do these warm-up practice problems. So as we did last week, you're going to have, these are the kinds of things I want to see that you're practicing. So you're going to, here's the first, there's 5 questions here. 1, 2, 3, 4, 5. So take out in your notebook, take out either a pencil or a 1-color pen, and then when you correct it, show me your corrections in a second color so that I can see what you did with and without my help. If you really have questions, you can write your questions in there too so I can see them. So go ahead and pause the video and see, and you can use a calculator or Desmos, right? You don't have to do these without those things. This would be a question where, the calculator would pop up on your exam and you could use Desmos right there, or use your calculator in your hand. Don't practice using with the calculator on your phone because you won't have that phone with you. You'll either have, if you're taking the exam on your phone, hopefully not, but you'll take the exam on your device and there'll be a little calculator Desmos you can use. So practice with Desmos or with like a TI instrument, and then when you're ready, hit go and check your work. All right, so for 61 here, I went ahead and graphed these and took pictures so you can see. It says, which of the following functions proves that there can be infinite number of solutions, right, for the equation at 0, right? So an infinite number of solutions. So ln of x, well, that's just one solution right there. And this doesn't look like it has any solutions. It looks like it has an asymptote. Here has one solution, so cosine x. So your answer should be choice B. So if you got it, give yourself a star or a smiley face. And if you didn't get it, right, maybe explain your error to yourself. The second one, which of the following functions proves that a bounded function can be increasing on the entire interval? So you can see why this is practice with the vocabulary. So a bounded function, right? So this is a bounded function, right? Cosine is bounded between here and here, but is it always increasing? No, sometimes it's decreasing and sometimes it's increasing, this function here is always going up, right? It's not actually bounded. It's going to, if I keep taking a bigger value of x, I'm going to keep having a bigger square root. It just slows down in how fast it grows. Same thing with the ln of x, right? This is always increasing, but it's not bounded. So this has to be our answer, right? Because it's always slowly getting, it's always increasing, but it's never passing 1. All right, so the C is our answer there. On 64, which of the following functions proves that a function can always be negative to the left of the y-axis and always be positive to the right, and yet decreasing over the interval in its domain? So let's look for the first part. Which one is always negative to the left and always positive to the right? Well, only this is negative to the left and positive to the right. This is not, right? It's not negative at all, so it can't be here. All right, so this is always negative and always positive, and this is always negative and always positive. So the only choice we got out is there. It says, and yet decreasing over the entire interval. So it's decreasing. So that means this isn't decreasing. This is increasing, right, over its entire interval. So look, this one, and it says over its domain. So there's part of here that it has no value, right, when x can equal 0, but decreasing, 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 then no value, not part of its domain, then decreasing, decreasing, decreasing. So 1 over x, right? And like I said, you could use your calculator to see these, or you could imagine them, but I think it's hard to imagine. It's easier to graph. All right, last two. Is every x-intercept of the cosine function a point of inflection? All right, so we need to remember point of inflection is where something changes concavity, so concave down to concave up, and there is a point of inflection at the x-intercept. All right, concave up to concave down, so yes, right? Every time it crosses the x-axis, it has a change in concavity. All right, so here we have, I forgot to get the question, 65, are there any solutions to the equation, right? And so we have to remember that solutions are when these two guys equal each other, right? So y equals x and y equals ln of x. So x equals ln of x, which would mean these two graphs should cross one another to have a solution, and they don't. So because these graphs never intersect, they have no solutions. All right, so stars if you got them, or smiley faces if you got them right, corrections if you got them wrong. All right, now we're going to review this rate of change, right? Constant rate of change. You've done this, y equals mx plus b, these straight lines. This rate of change is m. You have done this for a really long time in your mathematics career, right? It's a constant rate of change when we have a linear function, right? We can think of rate of change in the same way we think of that slope, that m, the slope of the line, right? How much is it going up and over or down and over, right? If we have a positive slope or a negative slope. And if we remember, right, you remember doing this since, I don't know, probably 6th or 7th grade, right, is this rate of change, which we can write it in a really crazy way. I want you to understand that when you see this f of b minus f of a divided by b minus a, it's no different than when you saw rise divided by run, right? The change in y, y2 minus y1, divided by the change in x, x2 minus x1, right? Our rise is our change in this y value. How much does it change here? And our run is how much does it change here? Well, y's are these, remember, if I have a function and I put some value in it, right? In the value is the x value, and when I evaluate it for that, that's the y value. So f of b is just a y value, and f of a is just a y value, and the b and the a is the x value. All right, so this formula, as complicated as it looks, is the same as you've seen, right, when you've been working with slope for a really long time. All right, so let's see. How can we do that? So it says, find the average rate of change between 1 and 2 and 3 and 4. All right, so let's see what you got. You try it, and then I'm going to go over it. So pause the video and see if you can do this, and then, because this is what you practice this week, and if you cannot, then I'll explain and you'll put it in a different color. So pause now and work on it. All right, so now we have this problem. So what are we doing here? We have the point 1, 2. That's something about here. And we have the whole function is a parabola, and we have another point 3, 4, which is something here. So average rate of change is just saying to find the slope of this line. That's all. All right, and because we're given the x and y values, right, I'm just finding the change in y, 4 minus 2, divided by the change in x, 3 minus 1. 2 divided by 2 is 1. The average rate of change is 1. So I go 1 up, 1 over, 1 up, 1 over to get to those 2 points. All right, so this should feel very, very comfortable because you've done this before. Now, we can get more complicated because what about the rate of change at just one point, right? So this is asking us, what's the rate of change for just x equals 1? What's the rate of change right here? Well, wait a second. To find rate of change, I need 2 points. All right, and I'm actually bringing up a video here that I'm always using with your extra practice because I think if you need extra practice for the week, these videos are fantastic. So I'm going to have him explain it because he does a really good job using a program called GeoGebra, which is a lot like Desmos. They're kind of interchangeable programs. But you can kind of see how would we estimate, right? Because it doesn't say exact, because you're going to, when you have to find the slope of a line exactly at a point, that's going to be something you do in calculus, and they're called derivatives. But you're not there yet. They just want you to understand, pre-calculus class, right? So they just want you to get this idea. So let's watch this together. And I'm going to fast forward it a little bit to the right part.
Sub it in our formula here. We're going to have the same formula. Y2, be careful, D25 point. What about the rate of change of a function at a point? This tells us about the rate at which the output values would change were the input values to change at that point. We can approximate the rate of change by using an average rate of change over really tiny intervals that contain the point. To illustrate this, what I'm going to do, here's our function that we were working with. I'm going to go to a website called GeoGebra. You might be familiar with it. And they have a graphing calculator that you can put in the function, which I did right here. And what I want to do is I'm just going to put 2 points. If you hit point, you can just click on here and I'll put a point on the function. You know, here are 2 points. And if I wanted to find the average rate of change, then I would find the slope of these two, right? I would find the slope. What I'm going to do is I'm going to put a line. How do we do that? Here's line. And I go through A and through B. Okay. So as we move these points closer together, suppose I want to know, I don't want to do that. Suppose I want to know what the average rate of change is at point A. Now, if you notice, look at the curve. It's pretty steep, right? I mean, because we're talking about the slope. And if I use point A and point B, then my estimate is not really going to be close to what the slope is right at point A. So what we're going to do is we're going to move this a little bit closer to A. And notice how this line, the slope of it, is pretty close to what the slope is at point A. And then after we move it that close, we're going to move it this close. And then we're going to move it this close. And if we get those 2 points very close together, then we can approximate the average rate of change at that single point as they become on top of each other and essentially become the same point. That's what we're going to do in this part of the packet. So it says estimate the rate of change at x equals 1. Okay, so to estimate the rate of change at x equals 1, I'm going to pick 2 points that are very close together. How about 1? We'll have x equals 1 and x equals 2. And I'll plug both of those into our function here. And if I do that, you can take my word for it. But I'm going to get, for x equals 1, a point of 1, 2. And for x equals 2, I'll get 2, 3.5. Now, sometimes I show a lot of work here. Pause the video if you need to some time, to write that down. But here's our slope formula, average rate of change. We work it all out. We get 1.5. And that represents the average rate of change between the straight line that would connect these points. That is the best job I could do. Not too bad. But estimating the rate of change becomes more and more accurate as these points get closer together. So instead of using an x value of 1 and an x value of 2, let's use an x value of 1 and another x value of 1.1. What would that look like? Well, to help us out, this is hard calculations. We're going to use our calculator. So I'm going to go back to the calculator. I've already done some stuff, but I'm going to quit. I'm going to show you. This is our first little calculator. If we do second and then memory, which is above the plus sign, and 712, that'll help us clear the RAM. You only have to do this if this isn't your calculator and you're not really quite sure how to, the settingness could be messed up. But I just cleared the memory out. We're going to plug in this function. We're going to make sure we use our parentheses. Where'd that function go? It's all the way over here. So use your parentheses, and it's -1/2. I always put parentheses around fractions. It's a great idea. Here's the x and the squared button. I'm just going to use this little caret. That works for exponents. You could also use this button right here. So we have -1/2 x squared plus 3. Go back to the x, and we subtract, use your parentheses, 1/2. All right, so here's our function, and we put it in y1. That's going to be important later. But if I were to go to the table, see where the table is here? It's in blue on mine. You hit second and then table. It gives you a table of values starting at 0. 1 is 2. We already knew that. And then 2 is 3.5. We knew that. So on and so forth all the way down. You can scroll down. You can scroll up as long as your cursor's on that input value right there. Well, that helps us plug numbers in. But what I want to do is get these points closer together. So I want to use x equals 1 and x equals 1.1. How can I come up with that 2.195, which is the output for 1.1? Now, there are ways you can change the settings in the table. So I'll show you how to do that right now. If we go second, table set. Okay, this first number tells you where you want to start the table. So -2 is, I guess, okay, but let's go down to this one here, which is the most important. It says delta table. Now, we learned earlier today, delta means change it. We want the table to change in tenths because I want to go to 1.1. And you know what? I could start this at 1. That'd probably make our life easier. So this says start at 1 and change by tenths. So if I go back to the table, check this out. It starts at 1 and it's changing by tenths, the input value. So that gives us our 2.195. Easy enough. Now, I could also do this as we work. Let's work this out. Work it out. Oh, there we go. Plug it all in. We get a slope of 1.95. That's if we have the 2 points so close together. If we move that all the way down to here, we get a different slope. It's a little more steep than it would be. As this point moves away, then the slope decreases. But as they come close.
All right, so I hope you can see that these kinds of rate of change problems are going to come in 2 different ways. One, they're telling you the points to use, right? In this problem, they said, we want you to use these points. And sometimes they're only going to give you 1 point, and your job is going to be to use points that are really close to that, right? That point and another point that is very close to it, all right? So, but the idea is still the same. You're still using, right? Either you can look at it as this formula or just the change in y divided by the change in x. Okay. A lot of times students ask me, how do I know I have a rate of change problem when I see words? So I want you to see that the word per is a key indicator that we are dealing with rate of change. Miles per gallon, students per classroom, online gamers per server. All right. So I want you to understand that these are telling you, I have something on the x-axis and something on the y-axis, and I have some sort of rate of change, right? And this also tells you which variable is dependent or independent, as the dependent is always listed first, all right? So this is miles per gallon, right? So the dependent variable is always listed first. So let's practice just a little bit with that, all right? So this is going to be, well, I add one more thing and then we're going to practice. So we can also talk about a positive rate of change, right? This would be a positive slope. So something going across the screen like this, right, is the x variable is going up, the y variable is going up, or as the x variable is going down, the y variable is going down, right? So a positive rate of change indicates that one quantity increases or decreases, the other quantity does the same. It increases or decreases in the same way. A negative rate of change, that one quantity increases, the other decreases, all right? Because we're going this way across the screen, all right? So pause the video now, read these 4 questions, All right, so state whether we have a positive or a negative rate of change going on. And then this is it. When you're done with this, we check, and you're done with the video. So write it in one color, pause the video, then check it in another color. All right, so here we have, right, a candy company uses pints of chocolate to make candy. The more chocolate they use, the more boxes of candy they produce. Positive. The amount of money in Josh's savings account decreases for each semester he attends college, right? So that's an increase. It doesn't say that, but each semester is going to be more. So he has less money the more he goes to college. Negative. As the number of cats Mr. Sullivan owns increases, the number of mice in his barn decreases. Negative. The amount of water Mr. Bush drinks decreases, the fewer the trips he needs to make, right? So one goes down, the other goes down. Two things going down is a positive slope, right? Down and this way, both decreasing, gives us a slope that goes across this way. All right, so turn in for me any questions that you have. And the evidence is you're showing you practice the problems in one color and you showed your corrections in another color. Thank you for working hard on this today.